Hey, my name is Michael and I'm a Chem 121 PLF. Today I'm going to be guiding you through molecular polarity. I picked each one of these molecules out because their molecular geometry is all different. We'll be considering carbon dioxide, boron trifluoride, methane, ammonia, water, xenon difluoride, phosphorus pentafluoride, selenium tetrafluoride, chlorine trifluoride, sulfur hexafluoride, chlorine pentafluoride, and xenon tetrafluoride. During this talk, I'll be talking about the steric number, whether it's polar or nonpolar, and both the electron and molecular geometries, as well as the bond angle. So our first molecule is going to be CO2. And for the first one, I'm going to go slow. We'll draw our Lewis structure, just the skeleton first. And we know based on the octet rule that every atom wants to have a full valence shell. For carbon, that's going to be 8. So we want 2 bonds on each side of carbon. And just remember that each one of these lines represents 2 shared covalent electrons between these 2 atoms. So we have 2, 4, 6, 8. We also know that oxygen wants a full octet. So we're going to have 2 lone pairs on oxygen for both sides. So now everything's satisfied. Is this molecule polar or not? Well, there's going to be a dipole that's drawn as an arrow with a perpendicular line through one end, and that end is the positive end. There's 2 dipole moments because there's 2 electronegative atoms, or 2 bonds. Now, these oxygen are more electronegative than carbon, so the negative side is going to be on this side, which is represented as the point of the arrow, and both of these will cancel out. That results in a 180-degree bond angle. Nonpolar molecule. Since there's 2 bonds in this molecule, it's going to have a steric number of 2. 180-degree bond angle between these bonds, as I said. And since there's no lone pairs on carbon, or the central atom, the electron geometry is going to be the same as the molecular geometry, and that's going to be linear. All right. So I'm going to move faster through the rest of these. I won't draw lone pairs. I will draw bond angles on most of them, not all of them, and I will try and draw the dipole moments. All right, boron trifluoride. Let's draw our Lewis structure. And just to not be ambiguous, I'll try and draw it as it would be represented in 3 dimensions. Except I won't be using dashed or wedged lines. I'll just be using straight lines for the bond angle. All right, so our dipole moments are like this. And due to dispersion forces, each one of these fluorines wants to be as far away from the next closest fluorine, and that's going to result in a plane formation. So all these dipole moments will cancel out for a nonpolar molecule. And since there's 3 bonding groups of electrons with no lone pairs, the SN steric number will be 3. And this will result in a 120-degree angle between each one of these bonds. No lone pairs means electron geometry is the same as the molecular geometry. And that's going to be trigonal planar for this molecule. Alright, methane. I'm just going to draw this one with a normal Lewis structure, not try and represent it in 3 dimensions. Central atom is carbon, hydrogen, 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 and hydrogen. Alright. So this is not how it'd be oriented in 3 dimensions per se. Each one of these dipoles will cancel out because they're equal and opposite. and that results in a nonpolar molecule. We have 4 bonding groups of electrons and no lone pairs, SN4, 109.5 degrees bond angle between each one of these, even though it looks different on the paper. And no lone pairs means the electron geometry is synonymous with the molecular geometry, and this is going to be tetrahedral. All right, ammonia is our next molecule. Now if we look at the periodic table, we know that ammonia has 5 electrons. It wants 8, so it gets 1 from each of these extra hydrogens. H, 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 and a lone pair 2, 4, 6, 8. It's happy. All right. So this has a lone pair, so it's polar, and the steric number of this is going to be 4, but since it has a lone pair, represent that as 3 plus 1. And that's going to give us a bond angle of 107 degrees between each one of these bonds. Since it's polar, the electron geometry is different from the molecular geometry, and our electron geometry will be tetrahedral. However, our molecular geometry will be trigonal pyramidal. All right. Water is next. So we have oxygen as our central atom, and we're going to have hydrogen quite like that. We know we need 4 more electrons, so 2 lone pairs. That's going to make this polar. Steric number is going to be 4, and it's going to be 2 bonding pairs of electrons and 2 lone pairs of electrons. And these lone pairs exert a force on these hydrogen bonds, and that's going to cause the bonds to not be in a straight 180 degree from one another linear pattern, and that'll actually be 104.5 degrees between these hydrogen bonds. Since it's polar, the electron geometry is different from the molecular. Again, steric number of 4 will be tetrahedral electron geometry, and the molecular geometry is going to be bent. All right, there's water. Xenon difluoride. Our central atom is xenon, and we have 2 fluorines. However, we know if we look at the periodic table, there's going to be 6 extra valence electrons around xenon, which just means there's going to be 3 lone pairs, and our dipole moment is going to be like this. So they will cancel out, and that results in a nonpolar molecule. So we have 1, 2, 3, 4, 5 electron groups. 2 of them are bonding, so that'll be 2, plus 3 lone pairs equals steric number of 5. And the angle between this bond is 180 degrees. Molecular geometry is going to be linear. And this the electron geometry of this will be trigonal bipyramidal. And I'm going to turn it on its side like this, and I'll talk a little bit about axial and equatorial. So if we think about, just think about the Earth. So it's a sphere, and the equator would be something like that. And here's the rest of it. Our axis is right here, and here's our equator. Electron pairs normally like to orient themselves equatorially around the central atom, if possible, with the ligands, which a ligand is any atom that's bonded to another atom. So xenon has 2 ligands in each one of the fluorines, and they'll want to orient themselves around the axis. So that's just some other terminology that's used commonly: equatorial and axial. Lone pairs are equatorial normally, and axial for the ligands. Sometimes ligands can also be equatorial, so it just depends on the molecule. I'm not 100% on the electron geometry of this. I think it's actually trigonal bipyramidal, because this would be a triangle right here, and then there would be a pyramid here and a pyramid here based on the electron geometries. I'm not 100% though. I think that's right. Anyways, we'll go on. It's just a tricky molecule. Phosphorus, pentafluoride. We'll draw our Lewis structure. We've got 5 fluorines. No lone pairs. And since there's 5 of these, we know that the dipole moment is not going to cancel out around this phosphorus central atom, which results in a polar molecule. We have no lone pairs. Our steric number is going to be 5 because of the 5 bonding groups of electrons. Phosphorus is a special case, one of several. And our bond angles, as I was speaking about before, we'll have an equatorial and an axial position. The bond angle between axial and equatorial would be 90 degrees. And our bond angle between our equatorial ligands will be 120 degrees. Our electron geometry will be synonymous with our molecular geometry, and that's going to be trigonal bipyramidal. And that's because there's no lone pairs. All right. Next we have selenium tetrafluoride. This molecule is kind of special in its shape, and I'll discuss why. So our Lewis structure will be something like this, and for the purpose of the shape of this molecule, I'll draw it kind of like that. All right, so we do have one lone pair on selenium. It's right there for this diagram. It's going to be polar. Our steric number is going to be 4 bonding groups of electrons plus 1 for 5. And we'll have 180 degrees about this bond angle and 120 degrees around that one. So our electron geometry is trigonal bipyramidal. And our molecular geometry is actually seesaw. Alright, why this is called a seesaw is because it kind of resembles one. If this is the central part of the seesaw, this is where somebody would sit right here on one side, and there's the handle for them to grip, and on the other side is the next seat for the person and the other handle, and they would just seesaw back and forth just like this, and that's why they call it seesaw. All right, chlorine trifluoride now is our next one. Here's our Lewis structure. So we know chlorine has 7 electrons. Here's 1, 2, 3, 4, 5, 6, 7. And actually, I drew this different than I should have. Anyways, I'll draw it again. Chlorine, fluorine, fluorine, and fluorine. 2 lone pairs. All right. So as you can see, this kind of resembles a T. So the molecular geometry is T-shaped. This has lone pairs. It's a polar molecule. Steric number is going to be 1, 2, 3, 4, 5. But there's 3 bonds and 2 lone pairs. It's going to give us 90 degrees bond angle and 120 degrees between the electron groups. Our electron geometry is trigonal bipyramidal, since the steric number is 5. Just gonna abbreviate it as this, trigonal bipyramidal, and molecular geometry is T-shaped. Sorry about that. Okay. So for our next molecule, sulfur hexafluoride, we're going to have 4 fluorines around its equator and 2 fluorines about the axis. All of these axial fluorines, their dipole moments will offset, and these equatorial fluorines will also offset, so that'll result in a nonpolar molecule. Steric number is going to be 6 because we have 6 bonding groups of electrons. and it'll be 90 here, and it'll also be 90 equatorially, axially and equatorially. No lone pairs, so the electron geometry and the molecular geometry are both going to be octahedral. Alright, we've got 2 more to go. Chlorine pentafluoride, central atom, 5 fluorines. One lone pair for 1, 2, 3, 4, 5, 6, 7 electrons around chlorine. It's got a lone pair. This is going to be polar. Steric number is 6. It's going to be 5 groups of bonding electrons and 1 lone pair. This will also have 90 and 90 angled between the bonds and the electron groups, axial and equatorial. Our electron geometry is octahedral, since our steric number is 6. And our molecular geometry is actually going to be square pyramidal, since there's going to be a square around the equatorial fluorines and then a pyramid around this fluorine right here. Alright. I'm running out of room, so excuse me writing off of the screen. I'll try and account for it after I finish. And xenon tetrafluoride is our last molecule. Got 4 fluorines. And we have 2 lone pairs. We're going to have a nonpolar molecule here. These electron groups cancel out the dipole moment around them, as well as the fluorines. Steric number is 6, and it's going to be 4 bonding groups of electrons and 2 lone pairs. 4 plus 2. We'll have 90 degrees between these fluorines right here. Our electron geometry is octahedral because SN number of 6. And our molecular geometry is square planar because these bonding groups of electrons are in a square plane. Alright, and that is all of the molecular geometries that you will ever encounter. The molecular geometry is largely dependent on the steric number, the electron geometry is largely dependent on the steric number of the molecule. However, the molecular geometry will change regardless of the steric number when there's lone pairs. So octahedral is going to be a steric number of 6. Trigonal bipyramidal is going to be a steric number of 5 for electron geometry. Steric number of 4 is going to be tetrahedral, 3 trigonal planar, and 2 linear. Now, thank you for watching. I hope this helps out.